Thank you. I hope this microphone works okay. I hope everyone can hear me clearly. So, as I was introduced, my name is Christiaan Brinkerink. I work at the Radboud Radio Lab in the Netherlands. We are connected to the Department of Astrophysics at Radboud University. And we are currently coordinating the efforts of the topical team on radio astronomy from the lunar surface. So we have a particular concept in mind for the kind of facility that we are thinking of, and I hope to introduce you to that today. So without further ado, let's dive right into things. So basically, we are thinking for ALO in terms of many element interferometric array to be deployed on the far side of the moon. And we are thinking of EL3 or the Argonaut lander to be used as a delivery and a platform from which to base the instrument. We are currently consisting of a group, a topical team that's about 70 people all in all, a mix between scientists, engineers, and interested commercial partners. And we have last year also worked on a study where we thought about a precursor instrument to this ALO, because as you will see, ALO is quite an ambitious and complicated project, and we need to get there in a few steps. So this is why we have been thinking in terms of precursor instruments that could go on an earlier launch as well. So what are we primarily focusing on? As I mentioned, we are the radio astronomy topical team, but there's one science case that clearly stands out as the top interesting science case that we want to pursue from the lunar far side. And this is the radio signal from neutral hydrogen in the early universe. So in this diagram above, you see the schematic evolution of the universe with this big blue region before star formation really got underway. So we typically term this the dark ages and the cosmic dawn, when the first stars start shining. And from this age, there's no starlight reaching us, but there is the radio signal from neutral hydrogen, which was, of course, already around. This is heavily redshifted as we observe it today, of course, which means that that 1.4 gigahertz signal is now redshifted into the range below 100 megahertz. So that is currently the biggest open question, is what was happening structure formation-wise in this early universe, and how do we best capture that kind of signal from here? Now, so the motivation for going to the moon is quite clear, right? On Earth, these frequencies below 100 megahertz are heavily polluted with RFI. We have the ionosphere in our way. And so you really need to step out of the Earth's atmosphere, go to a radio quiet place to do research into this signal. So what are our top science goals? As I mentioned, we really want to focus on this. While the interferometric array will be capable of measuring other phenomena at low frequencies as well, we really want to focus and basically design the concept around this science case. And we basically would like to probe the redshift range between Z equals 200 to Z equals 16, which covers all of the dark ages and the cosmic dawn. We would not only like to capture the global signal, the general spectral shape of the signal, as is outlined on the right here. So the red line gives a rough idea of how the signal couples to different physical processes throughout this early universe. Or the universe's history. So the global signal, there are experiments underway also from Earth that are attempting to capture the signal in a certain frequency range. But we also want to measure the spatial power spectrum of the signal, how it varies with the direction we look in and the depth we look at. So the global signal is something that a single well-calibrated antenna should be able to measure. But to measure the power spectrum, you need to be able to distinguish different spatial scales from each other. And also, of course, have sufficient sensitivity to probe into the spectral domain and see what kind of variations you encounter there. So the global signal requires a single antenna, but an extremely well-calibrated one, whereas the power spectrum measurement, the spatial variation of the signal, requires a full interferometric array to be able to distinguish these scales from each other. So what does this look like? Well, basically, an interferometer is sensitive to multiple spatial scales. I see I'm taking way too long for these slides, so I need to speed up. So you measure angles on the sky, you measure structure in frequency space, and that gives you a three-dimensional space, which you can average over in different shells to get different scale sizes for this power spectrum. So the general concept that we are currently looking at is a flat array of 32 by 32 elements, which is the minimum size we expect to yield scientific value for this study. And basically, 32 by 32 antennas means over 1,000 antennas in total, and deploying those from a single lander is extremely challenging if you think about classic antennas in the normal sense. So we need to think in terms of very, very lightweight antennas unrollable or inflatable structures that are deployed through some kind of hierarchical system from a central point. The antenna size has to be several meters to, couple efficiently to the radiation regime that we're interested in. And they need to be placed close together because that's actually optimal for studying the science case. We want to reach sufficient sensitivity over particular size scales on the sky, and that means the array needs to be compact. So some top-level system requirements. I'll very briefly go through the slide because it's just a few numbers, but we're talking about a rough payload estimate of about 1.5 tons. That's a safe estimate for the capability of EO3. And so the mass per antenna needs to be on the order of 1 kilogram at max for an antenna that's several meters in a linear dimension. Power consumption needs to be limited to a few watts per antenna, and so we need to think of ways to locally generate this power per antenna element. And they need to survive, of course, a wide range of temperatures, right? On the lunar far side, we are blocked from the Earth's RFI, but we are still exposed to sunlight every 2 weeks, half of the time. And that means the temperature range over which our electronics need to survive, being quite exposed as part of these lightweight antennas, is quite wide as well. So there's definitely development needed in this direction. I will skip over the other quantities here. They are derived from the top level requirements. And so how does this array generate its data? Well, we are thinking of using a rectangular, regularly oriented set of antennas in a nicely spaced grid. This means that instead of correlating every antenna with every other antenna, as you would normally do in an interferometer, we can take a spatial FFT per frequency channel and get instant sky images generated this way. And so this gives us snapshots of the sky. And if we understand our instrument well enough, we can interpret those images, do foreground subtraction, account for antenna performance variations, and thus get at the subtle background signal that we want to get the power spectrum of. Of course, accurate modeling of your sky and calibration of your array are extremely important. You really need to know the instrument quite well. So 2 years ago, we did a CDF study with ESA, and basically the result of that is with current technology that's mature enough to start developing in detail, we can do a 4x4 element array, not a 32 by 32 element array. So there's quite a difference between what is currently possible with existing technology and what we would like to have. And this is why we need to develop technology on several fronts to make this possible. So currently, the focus of our efforts relies on identifying these technology roadmaps and pursuing actual research into them. Another thing about deploying antennas on the lunar surface is that there's quite a few effects that we need to worry about in terms of how radiation interacts with the lunar regolith. So we are looking at low frequency radio waves, and these penetrate into the lunar regolith according to the properties we currently know of the lunar regolith. And that means that we will get reflected signals to some extent. We need to understand how this happens, how bad it gets, what kind of attenuation we get, how these modify the response of the interferometer. And so we really need to talk to experts on lunar regolith structure as well. So that's what I actually hope to do this week as well. So once the interferometer observes this power spectrum, you get all kinds of interesting phenomena that depend on your instrument response. And one of these is that part of your frequency space gets polluted by the strong foregrounds that we have, so the galactic emission and stuff like that. And this is because of the chromatic response of the array. So this is a very important thing that we need to simulate in more detail. And Sonia's talk later today will actually talk about this, about how to better understand the concept of the instrument so we can get ready for these kinds of effects. Because very small errors amount to very large errors that you make in terms of getting your scientific signal of interest out. So basically the bottom line is that the calibration needs to be accurate to well within 1%, which is way better than you normally need for normal radio observations that we're used to. But once again, Sonia in her talk, 2 talks after mine, will talk about this as well. So the current activities of the topical team are quite broad. We have research going on into various different sub-components of this technology development. So we're talking about the antennas, how to deploy them, what kind of substrate to put them on, how to generate power for all of these antenna elements. Do we do this locally? How do we synchronize the clocks? How do we get the signal out? How do we do data transmission? Being on the lunar far side means we need infrastructure to bounce our signal back to Earth. So that's an important step as well. So we hope to make use of commercially available communication solutions. And of course, the data processing is another thing that we need to be quite careful about. Anyway, I will stop there because I'm out of time. So thank you very much for your attention. And I hope to be able to chat with you guys later this week as well. Thank you.